Hello, welcome to Dr. Nakamura's lecture series on bridge engineering, number A-8. Chapter 10, Arch Bridges. The arch bridge was constructed even in the Roman era and still stands today. The Segovia Aqua Bridge is one of the good examples. The steel arch bridge can be used for long span. The Sydney Harbour Bridge has a span length of 503 meters. These are the beautiful arch bridges in Porto. A is a steel arch bridge, Ponte Maria Pier, which was designed by Gustav Eiffel. B is the Arabida Bridge, very slender RC arch bridge. 10.1 Introduction. The arch bridge has the characteristics such as 1. The arch member is subjected to compression and bending moments. 2. It has various structural forms. 3. It has superb aesthetics. 4. Large horizontal reaction at the supports. 5. Construction is a little bit complicated. Elements of arch bridge are shown here. The arch rib is the main member of the arch bridge and has a shape of semicircle, parabola, ellipse, or catenary. The height between the arch crown, top of the arch rib, to the bottom of the arch is called arch rise. The end of arch rib is fixed to the abutment. This end part is called springing. The space between the arch rise and the girder is called spandrel. 10.2 Types of arch bridges. A is a fixed arch bridge, which is used for stone bridges. The fixed arch is also used for steel arch bridges, but bending moment is very large at the springing. B is monohinge arch, where a hinge is inserted at the span center. C is the two-hinge arch, which are commonly used for steel bridges. D is a three-hinge arch, which is a statically determinate structure. This is a favorable solution for soft ground, but is vulnerable against vibration. E is a tied arch, where the both ends of the arch rib are connected with a tie. As the horizontal reactions do not exist, it does not require a huge abutment and favored at urban areas. The tie can be replaced by the girder, where bending moments occur in addition to the axial tension. F is the upper deck arch. The arch can be connected with the upper deck and the girder through vertical struts. G is a Nielsen arch, where the hangers and struts are inclined and crossed. This is aesthetic, but the control of cable pre-stressing is not easy. H is the balanced arch, where the reactions at the supports are balanced. The girder bending moments can also be reduced. I is the spandrel arch, where the space between the arch rib and the girder is connected by trusses. 10.3 Structural mechanics of arch bridges. When the arch rib shape is properly adopted, all the vertical loads can be supported only by the axial force of the arch rib. The arch shape must satisfy the equation 10.1, which can be obtained by the equilibrium equation. For the equally distributed load W, the arch rib is parabola and the horizontal reaction H is obtained by equation 10.2. As the design load fluctuates along the span length, not only axial forces but also bending moments occur in the arch rib. The bending moment M is obtained by M0 minus Hy, where M0 is the bending moment as a simple beam, and Y is the height of the arch rib. Exercise 10.1 Sectional forces of a two-hinge arch. Suppose that the equally distributed load Q is applied to a two-hinge arch with a span length L and the arch rise F. Obtain horizontal reaction H, bending moment M, and axial force N of the arch rib. The arch shape is a parabola. Y and phi are expressed like this. H is obtained by this equation. Then M is M0 minus Hy, which is 0. The axial force N is N0 minus H cosine phi, which is shown in this graph. Exercise 10.2. Suppose that the concentrated load P is applied at the center of a two-hinge arch with a span length L equal 100 meters and the arch rise F equal 20 meters. Obtain horizontal reaction H, bending moment M, and axial force N of the arch rib. The arch rib shape is parabola. Y and phi become like this. There is a formula for the concentrated load which gives H with Xi of A over L. In this case, Xi is 0.5 and H is obtained like this. Then we can calculate M equal M0 minus Hy, which is shown in this graph. Axial force N is obtained and shown in this graph. 10.4. There are some principles to be considered in the design of arch bridges. The steel arch bridge is widely used, in particular for long-span bridges. In general, the arch rise is about 1/5 to 1/10 of the span length L, which provides a good balance. The arch shape should be decided so that only axial force occur under the dead load. For the arch rib, a box section is usually adopted to secure the compressive and torsional rigidity. In addition to the verification of members, the in-plane and out-of-plane buckling of the whole bridge must be checked. At the springing and the connection part of the girder and the arch rib, stress concentration is likely to occur. These parts should be studied by FEM analysis to reduce the stress concentration. Hangers and struts are likely to suffer corrosion and fatigue, in particular near the sockets. These parts should be carefully designed. 10.5 Buckling of the arch bridge. A. In-plane buckling. When the arch rib is subjected to the distributed vertical load Q, it buckles like this. This is the in-plane buckling. The critical horizontal force depends on the bending rigidity, arch rise, the span length, and the buckling coefficient alpha CR, which depends on the type of arch as shown in this graph. B. Out-of-plane buckling. When the arch rib is subjected to the distributed vertical load Q, the arch plane buckles in the lateral direction like this. This is likely to occur for small ratio of width over length. The crossbeam and lateral bracing to connect the two arch ribs are effective way to prevent this. This buckling is usually accompanied by torsion. C. Geometrical nonlinear analysis. Linear analysis is used for short-span arch bridges. However, geometrical nonlinear analysis is used for long-span arch bridges. In this analysis, equilibrium equation is set up after deformation, which is essential to find the buckling strength. Material nonlinearity is also considered to obtain the ultimate strength. 10.6 Construction methods of arch bridge. The erection of arch bridges is, in general, a bit complicated. A is a cantilever method where the arch rib is erected from the end support towards the span center with a temporary stays. B is also the cantilever method using the truss members. C is a lowering method where the half of the arch rib is assembled upright at the abutment, then lowered to the horizontal position. This is the cable erection method used for steel arch bridges. The arch rib is erected from the end support towards the span center using the temporary cables which supports the arch rib. That's all for this lecture. See you next lecture.